You might have heard the term moment before, but what is actually moment? In definition, we can call it the turning effect of forces, but to explain it in better terms, we can also use the term torque. So, for example, I have a door over here and it is hinged at these points. Now, I want to place a doorknob anywhere on this door in the manner that it becomes easiest for a person to open that door. And as we all know, we are going to place the doorknob somewhere around here. Why so? Well, at this point, it is the easiest for a person to open the door. If it would have been this point or this point or this point, it would have been near to impossible for someone to open the door. And this is better explained by moment of a force or torque. So by definition, the moment of force is the turning effect created about a pivot in the line of action of force. Now, a little bit this is getting a little bit technical, and we're going to understand these terms and phrases as we move further on. So when we look at the formula, so the moment of a force is the product of force F and the perpendicular distance d from the pivot to the line of action of force, and hence we can say that m, or moment, is equals to force into a distance, where moment is in Newton meters, force is in newtons, and distance is in meters. Now, here we can understand the definition of moment. So I have a force, I have an object placed over here, and due to its own weight, which is a type of force, this is going to get disbalanced, the setup is going to get disbalanced, and the plank will move downwards. Now, here we have a distance from the pivot. This is the pivot. Pivot is the point about which a moment is created. So this is your pivot, and the distance from the pivot till the line of action of force, this is the line of action of force, the weight is acting downwards, is the perpendicular distance, and we multiply both of these values, the force and the perpendicular distance, to get our moment. So moment is this turning effect that is created about a pivot. What is a pivot then? Pivot is a fixed point. So in the previous setup, we saw that at the center of the setup, you had the pivot or the fixed point, and turning effect is created about a pivot. For example, a hinge, your door hinge, or for example, when you're using a spanner and you're trying to turn a screw, so your screw is the pivot. Now we have a few factors that determine the moment, that have an effect on moment. So the magnitude of the force applied, greater the force applied, greater the moment, and the perpendicular distance to the line of action of force. Greater the perpendicular distance, smaller the moment. So when we were talking about the door, we used the point that was greatest, that had the greatest distance from the hinge, and having the greatest distance meant that the moment will be the least, and hence you would require minimum force to open the door. Now, moment created can be clockwise or anti-clockwise. For example, in that seesaw setup that we saw a few moments ago. Now, again, keeping the idea about perpendicular distance in mind, say I have a spanner, and so obviously the screw is going to be here, and I am going to apply the same force. Which point should I apply force on so that it is easier for me to unscrew the screw? So it's going to be this point. Why? Because it has the greatest distance from the pivot. What is the pivot? What is the fixed point over here? The screw is the fixed point. Again, in a longer spanner and in a shorter spanner, in this spanner, you will have to apply lesser force to unscrew your nut. And over here, you'll have to apply a larger force because the distance is lesser. And so force and distance are inversely proportional to each other. Now, increasing your force increases moment or the turning effect, as we discussed. So, and we discussed that moment can be anti-clockwise or clockwise. So that means that moment is a vector quantity because it has direction, either clockwise or anti-clockwise. Now let's have a look at this example. So when you have different distances, the force will vary to keep this balanced. So to keep this wooden plank balanced on this pivot, this red triangle is the pivot. If we have a shorter distance d, then we need a larger force. So we're using more weights over here. And if we have a larger distance, then we need less forces to create the exact same moment, which is why I can say that F1, force 1 into distance 1 is equals to force 2 into distance 2, and they both are going to be equal. For example, I say that this is a force of 4 Newton, and this is a distance of 2 meters. And I say that this is double the distance, so this is 4 meters, and this is double the weight, so this is 2 Newton. To keep it balanced, moment, the clockwise moment, which is the moment on the right side, and the anti-clockwise moment, which is the moment on the left side, should be equal, and F1 D1 should equal to F2 D2. So 4 into 2 is equals to 2 into 4, 8 is equals to 8 Newton meters. It means this is balanced. What is the principle of moment? The principle states that when a body is in equilibrium, the sum of clockwise moments about a pivot is equal to the sum of anti-clockwise moments about the same pivot, what we just discussed right now. And so F1 D1 is equals to F2 D2. What is the unit of moment? It's Newton meter. N into M. It's not Newton upon meters, it's Newton meters, because we are multiplying force in newtons by distance in meters. So we have the very same example here again, and we need to find out this force, how much force is being applied over here, such that the setup is balanced. So since F1 D1 is equals to F2 D2, so the F1 is 20 into F2, which is 12, is equals to F2, which we don't know, we need to find out, into 8. And in this manner, we can find out the force to be 40 Newton. Now let's have a look at the conditions for equilibrium. When we said that the setup was balanced, it meant that there was equilibrium. So the resultant force is going to be 0 newtons. And the resultant moment, or hence the resultant moment, is also going to be 0 newton meters. Now let's come to another subtopic, which is the center of gravity. Center of gravity is the point in any object on which the whole weight is appearing to act. So if I'm saying that I have this object and this is its center of gravity, then all of its weight is acting upon this specific point, which is the center of gravity. And for uniform objects, your center of gravity will lie in the center. So this is a uniform object. For example, I have a cube. And so in the exact center of the cube, I'm going to have my center of gravity. So like we can see over here, we have a circle. It's a uniform object. In the exact center, I have my COG. In a cuboid, I have the COG in the center. In a kite, I have the COG in the center. And the weight is acting downwards from this center of gravity, the weight of that object. But when we come to non-uniform objects, we have a whole method to find the center of gravity. So the first step says that make 3 small holes near the edge of a lamina. So this is our lamina. For example, this is an irregularly shaped cardboard piece, and I want to find its center of gravity. I made 3 holes that I'll take care are going to be as far apart from each other as possible near the edge of the lamina, and then I'll suspend the lamina freely from a pin. So this is my pin, for example, and I've suspended it freely from that pin. And then I'm going to hang a plumb line from the pin in front of the lamina. So I'm going to use a pendulum. And when the plumb line is steady, then I'm going to trace this line on the lamina. So this line, I'm going to trace it here. Then I'm going to hang this point from the pin over here. This point is going to move here. I'll trace the other line for it. and then for the third point, and at the point where all of these 3 lines are meeting, I'm going to get my center of gravity. So this is the pattern. I had 3 different points. I hung a pendulum on all of these 3 points, and then I marked my lines, and where all of these lines are dissected, I got my center of gravity. Now let's have a look at this pencil. I know that if I blow at it very slightly or I touch it very softly, this pencil is going to fall. Why? Because it's not stably placed. So this setup is not at all stable for the pencil. However, if it was lying horizontally, I could have blown at it, I could have pushed it, it would have remained in the same position. It might have been displaced from its position, but it would remain in the same horizontal position. And so we come to the concept of stability of an object. That is a measure of its ability to return to its original position if it is slightly displaced. So if I had my pencil and I displaced it slightly, it would have fallen down and it would not have returned back to its original position. And so there are 3 types of stability: stable, equilibrium, neutral. 3 types of equilibriums: stable equilibrium, neutral equilibrium, and unstable equilibrium. So this is stable equilibrium. For example, you have an upright cone. You can move it, but it's going to remain in this exact position. And in this is unstable equilibrium. This is standing on a very small point, and if I move it slightly, it's going to fall down and it won't be able to revert back to its original position. And in this is a neutral equilibrium. It's going to roll over in the same position, in the same state, and so there is no difference. Let's have a look at the example of a glass over here. This is stable equilibrium. I'm displacing it, but it remains in the same position. This is unstable equilibrium, it fell. And now this is neutral equilibrium. It's rolling in the same state or in the same position. So what is stable equilibrium? Here's an example. It's going to return back to its own position. So the center of gravity is going to rise slightly. Why? I displaced it slightly, and so the center of gravity rose a bit, and then it comes back. The object returns to its original position, so COG returns to its original height, and the line of action of its weight is still lying within its base. First, it lied within its base. This is the base, and still it is lying within the base. This is the base. The moment about the pivot causes it to return to its original position. This is the pivot. This is the fixed point. In an unstable equilibrium, I pushed it. This was the pivot. The moment was too great that it fell. The COG drops and it does not return to its original position. The line of action is now outside the base. This is the base. And now the line of action is outside the base, and the moment of its weight about the pivot causes it to topple over. Now we have neutral equilibrium. I can keep giving it a push. The COG will remain same. The line of action will remain same. Nothing will happen. The COG will remain at the same height, and the line of action of force through the COG and the contact force, contact with the table or whatever plane we have, they are going to coincide, and the moment over here is 0. There is no moment, there is no turning effect created about your pivot, and it stays in the same position to which it is displaced. Now, how can we increase the stability? We can keep the COG as low as possible. How can we do that? In this object, most of the weight or most of the mass has to act at that point. So more of the mass is upwards in such an object, and so the COG could be here. But if I invert it, so the more of the mass is downwards, and so the COG is lower. And so lower the COG, the more stable the object is. So more mass should be packed at the bottom, and the base area should be as wide as possible. Now let's have a look at an example using a different kind of setup to explain stable, unstable, and neutral equilibrium. So in stable equilibrium, this is your the black one is your ball. You moved it here, it moved back to its original position, and then it went here, then back to its original position. So it is returning back to equilibrium or the original position. Over here, this is unstable equilibrium. If the ball rolled here or here, it cannot roll back to equilibrium. So this is unstable. And in neutral equilibrium, there is equilibrium at any point of displacement. You can move it here or here. It doesn't really matter. So that's it for a moment. Thank you very much.